Welcome to After Hours Engineering, Episode 10. In this episode, we knock out a few more instructions of the I-type set, the Arithmetic Immediates, and the loads. For the arithmetic instructions, we now deal with one register and an immediate instead of two registers. And for the loads, we can load a byte, a half word, or a word. So let's start with the arithmetics first. Let's go. You know the drill. We start with our data flow diagram here. We then move to the FSM. We make some modifications to the control matrix, write some machine code, and then run a simulation. So first up, we're talking about the I-type instruction, which is adding a RS1 register against an immediate value. So we'll use both of these muxes here to route our data in. So let's turn off some of the noise here. We'll turn off the memory and we'll leave everything else up and going. We don't need the PC either. So for the I-type immediate, we know that our instruction contains the RS1 operand in it, but it also contains an immediate value in it, and that is routed down here into our immediate module. We'll then extract out the value, expand it, and route it into our mux. So this all means that we need to control signals, the identical set of signals that we did with the R-type, but the signals will change. We still need the write back for the registry. We need to select which source we're coming in from the ALU out or the ALU register. We still need to select the appropriate RS1 output on this one, and we need to select the immediate on this channel right here. Both of those will be routed in. We'll select the operation that we're performing, plus no minus in this case. Immediates don't do subtraction. Shifting, logical shifts, you name it, setting a bit, that all routes into the operation of the ALU, and then we look at writing it back through here. Now we'll look at the FSM that supports what we just covered in the data flow diagram. Come over to the FSM. We can see our R-type here. We've already covered that. So let's enable the I-type immediate. And in this case, this is where we are adding a register to an immediate value. So A source is going to be the RS1 or RSA on my channels. The B source is going to be the immediate, and we'll apply some function based on function 3 and possibly function 7 and do a write back once that's calculated. Again, there's a short circuit in here for a no-op if the destination is x0. This is the one that the ISA actually specifies as the ubiquitous no-op instruction, not this particular one, but it doesn't matter, they're both no-ops. Now let's take a look at the HDL code that supports this immediate type I code or state path. So here we are back in the control matrix. The first thing we'll do is modify the decode statement to add in a new pathway for our instruction execute cycle, and that's right here. We're adding in the I-type immediate, which defaults to or is set to this IT ALU. This is the immediate ALU instructions. That will take us into the case statement and trigger the IT ALU state. And in here you can see that we set the loading of the ALU out register. We set our A source to the RS1 or RSA in this case. And our B source is that immediate value that's in the instruction itself. Then we do a few extra tests to see whether we're doing shifting logicals or shifting right, and whether we need to include these function 7 piece to it. Otherwise we just default to the function 3. As well, here's the short circuit test. We look at what the destination register is, and if it's 0, we immediately go into a memory read and a fetch and prepare to go to the next state, the fetch. That takes care of this one. Otherwise, we go to the completion stage, which is identical to the R-type in that we're doing a write back. We select our WD source, which is that ALU register, and we set our register load. And then we set up for a memory read and go to the next state, which is the fetch. This is the HDL for the I-type immediate. Let's write some machine code to exercise that instruction. In this case, we're going to add 10 to whatever's in x4 and write it to x2. This is the instruction in its bit format. We've got our opcode for the immediate, the destination, which is 2, our function is 0, and the rs1 value is 4. And here's our immediate with the value 10 in it. If we break that down into nibbles and then reassemble it in hex, this is the instruction, the machine code instruction itself, which we placed here. And of course we have our break statement. In order to run the simulation, we'll need to update our memory to load in this RAM contents here. So we come over to memory and we give it the path and the name of the RAM file, and then we're ready to go. We can run the simulation. Here we are in the simulation, and as always over here to the left side is our reset sequence, but what's different is our X4 register is preloaded with a hex value, 28, and we're going to add 10 to it, or A, and hopefully we get the value 32 out. So if we come over here to the beginning of the fetch sequence for the instruction, we've recognized on the falling edge that it is an I-type immediate instruction, and we pulled it in. Excellent. We move over here to the decode statement, and we know that we'll be incrementing the PC plus 4. That's what's happened, 4, and the next address is 8. But we're also setting the next instruction set state to ITALU. Excellent. Then we transition automatically to the execute state. Now in this state, here we are, we're in the ITLU, and if we look down here at our ALU is a combinational circuit. So all the values, flags, and signals that were set up, immediately the ALU begins responding to those. We can see here that the register file has fed into the ALU the 28. That's the X4 value from here, from this bank. We can also see that the immediate value from the instruction itself is now present on the input to the ALU. And again, because it's a combinational circuit, the answer is available immediately, and sure enough, it is 32. We then transition into the ITLU complete state, which is our write back state. And as we expect, the register write signal goes low, and we write into the destination register, which is X2, the value 32. Excellent. This instruction is doing exactly what we were hoping it would do. And of course, it then falls into the e-break instruction and goes into the black hole of forever. And there you go. That's the ADDI. Looking back at our FSM, keep in mind that this one path in our FSM is implementing all 9 of the immediate instructions. The add, the ORs, all the booleans, the shift lefts, and the set bits are all implemented all together in one path. Next up is the loading instructions, or the I-type loads. So let's turn off the PC, as that's really not relevant to this, and we'll talk about what it is. We have our instruction register has been loaded with a load instruction, and part of it is going to have the destination register to where we're going to load the data, and we're going to pull it from memory. So once the instruction comes in here, it's selecting the destination, but we're also specifying the RS1 as a base register and immediate to add to that RS1. So both of those will route in here. That means we need to control these 2 signals and now this one. They're routed into the ALU. The address is calculated and loaded into ALU out, and then it comes around here and is presented to the memory. Now this is once the memory fetches the data out, we then route it into the memory data address register through the MUX and then into a specific register specified by the RD one. So that's our task. And knowing that, we know all the signals that we need to control. The address, the read, this load, this selector, this writer, these 2 muxes right here, this operation, and this load. So that's quite a bit of signals that we're going to be controlling with this. So having seen that, let's take a look at the FSM. Here we are back at the FSM, and we can see our R-type and our I-type immediate, the one we just covered. So let's enable the I-type load. Again, that's coming from the decode state, and we'll be making updates to that to route the path down here. So let's take a look at that. We know that on the load, we were looking at that diagram, we set up our ALU to add the RSA or the RS1 plus the immediate. This is going to calculate the address of where the data is coming from. We then read that data from memory, we route it through the MDR register, and then we complete the cycle by writing it to the register and setting up for returning back to the fetch cycle by bringing the memory read active. This would be the I-type load. And we'll do this for all the type byte sizes, like loading a byte, loading a half word, or loading a word altogether. Now we return back to the control matrix to modify the HDL. And of course we start with our decode statement. We come down here to our I-type load, and we notice that we're not setting any IR state. And that's because the default behavior of our combinational circuit is to set it to I-type load. So we're already set up and ready to go. We can collapse that and move down to the execute state, which is what's next. We'll scroll down until we see the IT load instruction. And there you can see from the FSM that we're loading our ALU out. We're setting the A source to RSA, which is RS1 in this case. The B source is being set to the immediate value, and then we transition to the memory access. There we set our read low, we select the address coming from the ALU out, and we set our memory. We go to the next state, which is the memory MDR register. There we maintain the read state and the address source, but we set the MDR load flag to enabled, and this will then load the data coming out of memory into the MDR. We then transition into the complete state, where we then do a write into the register file, and then we transition, or we prepare to go to the next fetch state and pick up the next instruction. So there we have it. This is the HDL code that supports that FSM diagram. As a quick reminder of what the memory management unit is doing for us, is that, remember, when we're loading different types of data sizes from memory, we need to sign extend what we're loading. If we're loading a byte, then we need to grab the sign of that byte and sign extend it into the output. Same thing for a half word. We would sign extend it only with 16 bits. And if we're just loading a word, we don't do anything. We just pass it straight on through to the output. So keep in mind the MMU is doing a bit of work for us in bringing the data in from memory. Now we write the machine code for the instruction. In this case, we'll start off with loading a word, which contains a destination register and immediate added to a base register. In this case it's X0, so we'll load directly from address 28 in byte addressing. This is the opcode bit codes for this. So we have opcode here, we have the destination, which is a 1. This is a function 3 is split up into two parts. The lower 2 bits defines the size, and the upper one is the sign bit. Then the offset base register, which is X0, and the immediate value that we're going to add to RS1's content. And there's 28. If we assemble this into nibbles and then form the instruction, we end up with this value right here. And there's the load word, and of course we have our break instruction. This is memory location 28, and we're going to be loading dead beef into X1. So when the simulation runs, we should see dead beef in X1. So here we are in the simulation for the load word instruction. We can see that the fetch cycle has started, and we've recognized that it's an I-type load instruction. And there is the machine code that we wrote. Excellent. And we loaded it from address 4, which is where the first instruction is occurring at. The next thing to look at is we are loading the destination register based on the offset plus the RS1 register. And so our ALU is being set up with the X0 being our base and the immediate value being added to it. And there you have it. Right there is the address of where the data is located. And you can see here on the memory access that the address is routed through the MUX and into the MMU, which we then turn around and read out what's in there on the falling edge of the clock here. And that's exactly what we were expecting. So here it is. Now, one thing to notice in this green area that I have highlighted here is that when we're trying to load registers, we really need to hold the data, the setup time, and the hold time. The problem with trying to read it straight out of the MMU is that on the falling edge, we're moving into the fetch state, which means we're also going to wipe out the previous address, and it's now loading with this address, the next instruction, which is the break instruction. And we don't want to load any of our registers when data is changing like that. And that's the exact reason why we have the MDR, the memory data register. That allows us to hold on to the data much longer while we are transitioning over to the next instruction. And so we are loading this version of the data into the X1 register, and that's what we see here. And that's exactly what we expect. So this is a good example of why the MDR register exists, because we don't want our data changing on us as we're trying to load it into different registers, in this case the register file. So that's all happening as expected. And of course we have the eBreak instruction, and it goes into the black hole. But here's the simulation for the load byte. It's identical to the load word, as you can see here. Even all the ALU is the same, and the address. But what's changed is the fact that we're loading in a signed byte. And the MMU, remember when we looked at the code, it was sign extending them based on the function that was passed in. In this case, it's a byte. So the function 3 would be 00. And so it saw that the EF that it's trying to load in, the lowest byte here, the bit is high because it's an E. And so it sign extended it out. And again, that's what we load into the MDR, which is then eventually loaded into the X1 register. So we've loaded a byte and sign extended it all into the register at once. So it doesn't say dead beef, it's a bunch of F's and then an EF. That's the load byte signed. Here's the simulation for the load byte unsigned version. And everything's identical, same address, same ALU functionality, but this time we are loading unsigned. So even though the high bit on the hex E is 1, we don't sign extend it. It's just simply loaded with all zeros, 0 filled. And that's exactly what we load into the MDR and what we load into the destination register. So this is identical. All that we've done is changed function 3 to all zeros, and we've changed the functionality of how we're loading data from memory. And of course we hit the black hole over here and we're done. Okay, we completed a large chunk of the I-type instructions, the immediates and the loads. As mentioned in a previous episode, I'm not going to be implementing the eCall instructions or any of the system calls to their fullest. However, I will be implementing the JLR, which is the last of the I-type instructions, and we'll do that in the next episode. So until next time, peace!